Hi, good morning.
Good morning, sir.
Good morning. Good morning. So we may start the session.
We can start.
Yeah, we can start.
Okay, let me. So I want to talk about something that concerns adaptive beamforming. So we go back to previous chapter because there is something I initially skipped because I was not sure to have time. Now I think we have enough time. So I would like to say something about a generalization of Capon, which is called linearly constrained minimum variance. Now, if you remember Capon, the minimum variance distortionless response beamformer, which is an adaptive non-parametric beamformer, can be designed by solving a minimization problem like this. So this is the power at the output of the beamformer. So this term here, if you remember, measure the contribution of the interference coming from different angles from the steering angle at the output of the beamformer. And obviously we want to minimize this contribution. And so this is the minimization problem of Capon, but with Capon we had only one constraint, a distortionless constraint. And the constraints was saying basically that if a target is coming from the steering direction, a signal is coming from the steering direction, we want this signal to pass undistorted. Now, sometimes it is possible that we need to impose additional constraints. So not only a distortionless constraint, but for example, we want to put some nulls in some direction. So remember, we talk about the null steering method. That method was not adaptive. Now, the idea is basically to implement in the adaptive beamformer also the null steering capabilities. How can we do that? Simply, we can increase the number of constraints. So, for example, if you have capital L linear constraints, you can write these constraints in this way. So instead of having a vector Hermitian H equal to 1, we have a number L of constraints. So if you call, for example, Ci the ith column of matrix C, the ith constraint is Ci Hermitian H equal to, it depends which kind of constraint you want to impose. If you want to impose a distortion constraint, this should be equal to 1. If you want to put a null, this should be equal to 0. So in general, another reason for imposing additional constraints is, for example, to stabilize the main beam response. So in order to limit the effect of an error in the pointing direction, we may want to build a beam that in the steering direction is almost flat. This can be obtained by imposing multiple constraints, multiple distortion constraints, corresponding to angles that are very close to the steering direction. So, I mean, there are different reasons why we may want to impose multiple linear constraints. Now, suppose that the number of constraints is L. you have to write the constraints in this form here. So the matrix of constraints C, Hermitian, that multiplies the impulse response of the beamformer, equal to B, where the elements of B are equal to 1 or 0, depending on the kind of constraint that you want to impose. So at the end, the matrix of constraints C is an M by L matrix. So M is the number of sensors. So it's the number of degrees of freedom, because it's the number of the elements of vector H, and L is the number of constraints. So at the end, the optimization problem with constraint that we want to solve can be expressed in this way. So it's very similar to Capon, but what is different is that you don't have a single constraints, but L constraints. So C, instead of being a vector, is a matrix. This beamformer is called linearly constrained minimum variance beamformer. So LCMV. Now, if you solve the problem by using the Lagrange multipliers, so I skipped the derivation, but it's identical to the derivation of Capon, and you find the solution. This is the solution. So the solution depends on the covariance matrix of the data. And so, I mean, it cannot be implemented as it is, but it should make adaptive. So we should replace in the expression the beamformer Ry with its sample estimate. And so in this way, we obtain the adaptive version of the linearly constrained minimum variance beamformer. Now, as I told you before, the constraints or point constraints, so we fix the answer of the beamformer to signals coming from certain angles to be either 1 or 0. So we impose a distortion constraint from some angles, and we put nulls at some other angles. So depending on this, the matrix C and the vector B can be made either, for example, like this, where we impose 5 different distortionless constraints, or like this. So we impose a distortionless constraints from angle theta t. So basically, we want to steer the beam in direction theta t, and we want to put nulls at direction theta j1, theta j2, theta j3, and so on, because we expect a jammer and interference from those angles. And as I said before, if you choose angles theta t1, theta t2, theta t3 that are very close, so that are distributed in a close neighborhood of the steering direction, the effect of imposing a constraint like this is to enlarge a bit the main beam. Obviously, you lose something in resolution, but you reduce the risk of an error in pointing direction. So you may need to do this to make the beamformer more robust to error in pointing direction. Now, what is the main drawback? The main drawback is the following: we have m degrees of freedom. So because the degrees of freedom is the size of the beamformer impulse response H. So we have m degrees of freedom. If we impose L constraints, the number of degrees of freedom decreases, because at that point we have m minus L degrees of freedom. Any constraint that you add reduces the degrees of freedom. And in practice, you have less degrees of freedom that can be used to minimize the power of the interference at the output of the beamformer. So a result of imposing too many constraints can be a rise and increase of the side lobes. And this is clearly something unwanted. So you should be careful when you impose multiple constraints. You should check the side lobe. Clearly, the beamformer that you obtain by solving the constraint optimization problem by using the Lagrange multiplier is the clairvoyant beamformer. So the one that knows a priori the covariance matrix of the data. Then once you have your clairvoyant beamformer, you can derive the power beam pattern, which is defined in the usual way. So the power beam pattern is the output of the beamformer, so the output of the filter, when at the input we have a source signal coming from direction theta t. And if you make the replacement, this is the expression of the power beam pattern. And in the same way, you can calculate the power of the output, and this is the expression of the power of the output. Now let's skip this derivation and let me show directly some numerical examples. So for example, this is the power of the output. So we are plotting here the power of the output, this one, as a function of the directional arrival of the source signal. So for example, we impose a distortionless constraint at these 5 angles. The input to the beamformer is a source signal coming from direction theta t plus additive white Gaussian noise with signal to noise ratio of 30 dB. The array is a Euler array made by 16 sensors, and this is what you get at the output. So you can see that all the times the target is coming from one of these 5 angles, you get a peak. Another possibility is to impose a distortion constraint and a null for these 5 angles. And this is the output power. I mean, this you don't see the 4 nulls because this is not the beam pattern. So when you point the beam in one of these directions, for example, 0 degrees, you don't get exactly 0. Why? Because you kill the directional signal that is coming from 0 degrees, but then you have the noise that enters from the side lobes. So that's why you have this constant level. This constant level is the contribution of the noise that enters from the side lobe. But then when you point the beam, when the target is coming from minus 60 degrees, which is the pointing direction, obviously you have a peak. So this is to explain this example. So what I plotted here, be careful, is not the beam pattern, but the output power. Now, you can also plot the beam pattern if you want. I mean, this is the output power, this is the beam pattern. So you can plot as well the beam pattern. Sometimes we want the shape of the beam pattern around the steering direction to be flat in order to reduce the sensitivity to pointing direction errors. And in order to achieve this, sometimes we impose also, in addition to point constraint, we may decide to impose also derivative constraints. So we impose, for example, that the first order derivative and the second order derivative around the peak is 0. So this is possible. Sometimes, in addition to find point constraints, you find also derivative constraints. The problem is that, so, I mean, the goal is the one to shape properly the beam pattern. The drawback is that the imposing of derivative constraints requires very accurate array calibration. So we should know the array response very well, because when you calculate the higher order derivative, basically an error in the knowledge of the array response is somehow magnified when you calculate the derivative. So, I mean, this is just to mention the fact that they exist. I will not spend time on this. Obviously, this is the expression of the clairvoyant beamformer. Then in practice, I mean, we use its adaptive version where the covariance matrix of the data, Ry, is replaced by the sample covariance matrix estimate. And for the reason that we have understood, you may use the diagonally loaded version of the sample covariance matrix estimate to improve robustness of the beamformer. So, I mean, as a final remark, remember, the more constraints you impose to stabilize, to shape the main beam, and the less degrees of freedom you have available to keep low the side lobes. So if you want to avoid that the side lobes becomes too large, it means that you need a number of sensor that is large enough with respect, it should be much greater than the number of constraints that you impose. So, I mean, there is always this trade-off between robustness and sensitivity, in the sense that the more constraints you try to impose on the main lobe, and the less degrees of freedom you have available that should be used to suppress the interference. And so the less degrees of freedom you have to shape properly the side lobes. So the choice of the constraints and the number of constraints is a trade-off between different needs. So the need of shaping the main beam, the need of maintaining low the side lobes. I want to close this part on adaptive beamforming by talking about what is called generalized side lobe canceller scheme, which is basically the canonical architecture used to implement any adaptive beamformer, and in particular, the linearly constrained minimum variance beamformer. So this canonical architecture is called generalized side lobe canceller. This is not a different beamformer, but it is an efficient way to implement the LCMV beamformer. Okay. So we start from the expression of the linearly constrained minimum variance beamformer, this one. Then imagine to decompose the beamformer in two terms by projecting this vector, at the end this is a vector, on the subspace generated by the column of Chi and on the orthogonal subspace. So if you remember, if you calculate C multiplied by this matrix, that is the Moore per rows pseudo inverse of C, what you get is a projection matrix. So when you multiply a vector by the projection matrix PC, what you obtain is the orthogonal projection of this vector onto the subspace generated by the column of Chi. So it's the set of all vectors that can be expressed as a linear combination of the columns of Chi. Now, the dimension of this subspace is equal to the rank of PC. So PC, in general, is a matrix which is not full rank, and the rank of this matrix is equal to the size of the subspace where the vector is projected. PC plus PC orthogonal is the identity matrix. So you can imagine to have here the identity matrix, and you express the identity matrix as the sum of the projection matrix on the subspace generated by C plus the projection matrix on the orthogonal subspace. You can always write this, and remember, C is the matrix of the constraints. So in particular, because PC orthogonal is the projection matrix on the orthogonal subspace, it means that if you multiply any column of C, so if you multiply the matrix C by this projection matrix, you get 0. So there are two terms, PC that multiplies this plus PC orthogonal that multiplies this, okay? Now, let's look at the first term. The first term is this one. Now, if you write explicitly PC, so PC is this one. So if you plug in PC this expression, you get PC, that is this one, R2 minus 1, C, and then the inverse of this. Now, if you look, this is the inverse of this. So the product of these two is the identity matrix. So at the end, the first term is this one. So the first term that we obtain from this product is this one. And the most important thing that should be observed is that this term does not depend on the covariance matrix. So this term basically can be implemented because it does not depend on Ry. So we does not need to implement this part of the beamformer in adaptive manner. When you make the replacement Ry with the sample matrix estimate, the replacement is only in the second term. So the first term, I repeat, is not adaptive. So basically, we have decomposed the impulse response of the beamformer as the sum of two terms. And the first terms as the very important property that is not adaptive. And then we have the second term, the one that, in order to be implemented, should be made adaptive. So we should replace Ry, which is unknown, with the sample covariance matrix. But we can make an observation. If the data are wide, so if the correlation matrix Ry are proportional to the identity matrix, the second term is 0, because you get, so this becomes the identity matrix, and so you have PC orthogonal times C. This is 0, so this term disappears. So the second term, which is adaptive, is present only if the data are not wide. The first part, which is not adaptive, basically represents the beamformer that we get if the data are wide. So if the samples collected at different antennas are spatially uncorrelated. So this term is called quiescent weight vector. So it's the beamformer that we would obtain, it's the non-adaptive beamformer that we would obtain if the data are wide. Okay, now let's call HQ this quiescent beamformer. So we can express the LCMV beamformer as the sum of two terms. Now, the first term is called HQ, and I repeat, is the quiescent, is the so-called quiescent beamformer. So it's a m-dimensional vector. And then we have the second term. Now, the second term can be expressed. So let's express the second term, which is given by this expression, but let's express this term in this way. As the product of a matrix where the size of this matrix, B is a rectangular matrix of size m by m minus the number of constraints, and this is called blocking matrix because B should have the property that B Hermitian C is equal to 0. And HA is the new vector that depends on Ry, obviously, because this represents the adaptive term. So is the new vector that should be made adaptive of size m minus n. So I repeat, we can always express the adaptive part of the beamformer in this way, where B is a matrix that is orthogonal to C. Now, in this expression here, you have PC orthogonal. So B, for example, could be equal to PC orthogonal, and HA could be this one. So if you plot the beamformer by using this representation here, we have the m-dimensional spatial vector. So the bold line means that it's a vector of size m. So we have the signal coming from the m sensors. We send the signal, so we multiply. So the output of the beamformer is H Hermitian Y. Now, because we have decomposed H as the sum of HQ and BHA, we can express the output of the beamformer in this way. So we calculate the Hermitian of H. So we have the Hermitian of this and then the Hermitian of this multiplied by Y. So we have HQ Hermitian Y minus HA Hermitian B Hermitian Y. So this is what is reported here. So in other words, we take Y, we multiply by this, and we get the output. Below, what we get, the output of B is this vector, which is m minus L dimensional. So B Hermitian Y is m minus L dimensional. And then we multiply by this, and we get this other scalar, and from the difference, we get the output of the beamformer. Now, basically, what is the interpretation of this scheme? The interpretation of this scheme is the following. B is what is called blocking matrix. So, in other words, it has this property. So this means that if you want to impose that the signal coming from a specific direction passes undistorted from the beamformer, it does not pass in the branch below because it is cancelled by the blocking matrix. So if a signal belongs to the subspace generated by C, so the direction for which we have imposed the distortionless constraints, these signals are blocked by matrix B. So they don't pass. So what we want to allow to pass the output cannot be cancelled here because it passes through here, but is blocked by the blocking matrix. So what is passed to the blocking matrix is only the interference. The interference is filtered by this adaptive beamformer and cancelled for the superior branch. So basically, the lower branch has the purpose to estimate the interference coming from angles different from the steering direction or the direction for which we have put the distortionless constraint. So we estimate the interference from coming from different direction and we subtract. In this way, basically, we minimize the contribution of the output of the interference. The role of the blocking matrix is to block the signal of interest because we don't want the signal of interest to pass through this matrix pass through the beamformer, subtracted and cancelled from the data, because we want the signal of interest to pass undistorted at the output. So how should we design this blocking matrix B? The only constraint is that B Hermitian C should be 0. So for example, we could choose B equal to PC orthogonal. So if you choose B equal to PC orthogonal, B is equal to this. But this is not the only possible choice. Actually, typically, it has been shown that it's better to select B as a full rank matrix. So it cannot be a projection matrix, because a projection matrix is non-full rank. So to reduce the sensitivity of B, it's better to choose B and not a full rank matrix. So it's better to choose B different from this projection matrix. And I will show you one example. So, but what is important is that B Hermitian times the matrix C of the constraints is equal to 0, because it should block the signal coming from certain direction. We want to pass only the interference because we want to measure the contribution of the interference and then to subtract it. Now, this beamformer here is not adaptive. The one that is adaptive is this one, but the advantage is that the size is smaller. It's not M, it is M minus L. So, the goodness is that since the size is smaller, we need a number of snapshots. Remember, the number of snapshots should be at least twice M. In this case, the number of snapshots should be at least twice M minus L. And so we need less snapshot to achieve close to optimal performance. Or in other words, the convergence of the adaptive detector is faster because the size of the impulse response is smaller. Now, how do we design H? So, HA. So the weight vector then should be made adaptive, and which has the purpose to suppress interference. Because it has to suppress the interference, basically we design the adaptive beamformer HA by minimizing the output power, exactly as we have done with KCON. So this is the whole beamformer impulse response, Hermitian Y. The modulo square is the output power. We take the expectation, we get the output power, and we want to minimize this quantity with respect to HA. So HQ is fixed, is non-adaptive. The unknown vector is HA, which is the adaptive part. So we calculate this term here. You calculate all the product. Then you calculate the gradient with respect to HA. You set the gradient equal to 0 and you find the solution. So basically, this is the optimal HA, and then in practice, it should be implemented by making it adaptive, so replacing Ry with the sample covariance matrix. And B remember, is the blocking matrix that should be chosen in such a way B Hermitian C is equal to 0. Now, this result actually is basically nothing but the Wiener filter. Because if you go back to this block diagram, so we want to optimize this. We want to find the impulse response of this linear filter that, based on the observation of the input data Z, minimize the difference between the output of the filter and YQ. And this is exactly the Wiener filter formulation. And the solution is the inverse of the covariance matrix of the data that multiplies the cross correlation vector between the data and the desired signal YQ. So RZ is the covariance matrix of the data. You calculate this expectation, you find this solution. The cross correlation between Z and the desired signal is this one. And so the optimal HA that we found is nothing but the solution of the Wiener-Roth equation. So remember, the expression of the FIR Wiener filter is the inverse of the covariance matrix of the data that multiplies the vector of the cross correlation between the data and the desired signal. So the solution that we derive by solving the optimization problem, so by calculating the gradient and setting the gradient equal to 0, is exactly equal to the solution of the Wiener-Roth equation. So it's the best linear minimum square error estimator. It has the property, all the nice property of the Wiener filter. And you can calculate the output power and the output signal noise ratio. So this is the output power, which is the power of the interference. And so the power of the signal divided the power of the interference is the signal interference plus noise ratio at the output of the beamformer. And you can see that the more Z and Y and YQ are correlated, the larger is this term that you subtract on the denominator, and the larger is the signal to interference plus noise ratio. So just a numerical example. So how to choose B? I mean, there are many possible choices. What is important is that B Hermitian C should be equal to 0. So for example, let's assume, to make it simple, that we have just a single constraint. So for example, we want to steer the beam in direction theta equal to 0. So if you want to steer the beam in direction theta equal to 0, the array response calculated at theta equal to 0 is 1, 1, 1, 1. So the vector, the matrix C becomes a vector because the size is m by L, and in our case L is equal to 1. B is an L-dimensional vector, so it becomes a scalar. So this is the distortionless constraint. And one possibility, so the size of the rectangular matrix B is m by m minus 1. And so you can see that one possible way to choose B in such a way that B Hermitian C is equal to 0 is this one. 1, 0, 1 minus 1 and then 0, 1 minus 1 and then 0, and so on. So you have all ones and minus ones. And note that this is not a square matrix, this is a rectangular. So with this choice, for example, the constraint B admittance C is equal to 0, and this is a full rank matrix. If you calculate the output of the beamformer, for example, when we have a single target, a single source, and signal to noise ratio 30 dB, this is what you get. So you get a very clear peak at 0 degrees. So any signal coming from an angle different from 0 is attenuated. And if the signal is coming from 0 degrees, we have a peak. And you can see that the beam is very narrow, and basically also the effect of the side lobe is negligible. Remember, this is not the beam pattern. This is the beamformer output in the presence of signal plus noise. So the difference is the presence of the noise, okay? So the beam pattern basically is the output in the absence of noise. So the general side lobe canceller is not a different beamforming, but it's an efficient way to implement the linearly constraints minimum variance beamformer. So it's an efficient implementation of the LCMV beamformer. And they have called this architecture generalized side block canceller because the structure reminds a bit the structure of the side lobe canceller, where you use basically you have two channels. In one channel, you measure the power coming. Basically, in the side lobe canceller, you have a small, an omnidirectional antenna with a small gain. And the purpose of this antenna is to understand if a signal is coming from the main lobe or from side lobe. And if we understand that the signal is coming from the side lobe, that signal is canceled. So that's why it is called side lobe canceller. It's an architecture that has the purpose to cancel the signal entering in the beamformer through the side lobes. This architecture that I just described in some way is similar to the architecture of the side lobe canceller. Because the lower branch has just the purpose to measure the interference that enter through the side lobes, and then this contribution is canceled from the upper branch. So that's why it is called generalized side lobe canceller. If you are familiar with the side lobe canceller, you can recognize the similarity. Okay, I think we can stop here. There are other kinds of beamformer. In this view graph, I mentioned the eigenspace-based beamformer, but I did not describe in detail. So if you are, I mentioned just because if some of you are curious, can find additional information in the web. Okay, I would stop here this part. I just wanted to mention the concept of linearly constrained minimum variance beamformer, which is basically an extension of Capon beamformer when we want to impose multiple constraints. And I introduced the concept of generalized side lobe canceller, which is the canonical architecture that is implemented for the linearly constrained minimum variance beamformer. I repeat, is not a different beamformer. It is just an efficient way to implement the linearly constrained minimum variance beamformer. And why it is more efficient? Because basically we separate the non-adaptive from the adaptive part of the beamformer, and because the adaptive part has size smaller than m, actually it is m minus L, the number of constraints. This allows the beamformer to converge faster, because the number of snapshots that we need is proportional to the size of the impulse response of the beamformer. And so if the impulse response of the adaptive beamformer is m minus L, which is smaller than m, the convergence is faster. Or in other words, we need less snapshot to achieve close to optimal performance. Okay, I think it's a good time to have 15 minutes